Hi and welcome to video 7 in this series on forces of motion using differential equations. This is to do with Unit 4, Topic 2 of the Specialist Math curriculum. So in this video I'm going to talk about forces and just review some forces, in particular force diagrams. In general, you'll need to recall that a force is a quantity measured in newtons, and of course it might be nice to recognize here that newtons is kilograms meters per second squared. Forces can act in three dimensionals, but we deal with only two dimensions. A force is a vector. The magnitude of the force has to be considered as well as the direction, and that's important. Multiple forces may be applied at once, in which case we have a resultant force. And if the resultant force is 0 newtons, then the forces are said to be in equilibrium, and the object or particle or whatever it is will not change its motion. So for example, if the resultant force is 0 newtons on an object that is currently stationary, it will remain stationary. But if it's moving with a certain velocity, the velocity won't change because the force affects the acceleration. And you've probably seen that, but we'll get to that in more detail. So force diagrams. There are two ways that we might solve or resolve a force diagram to solve a problem. And the first way is diagrammatically using resolving into components, and to be honest, this is, as far as I'm concerned, by far the best way. So to resolve into components, we consider our very well known I and J components here, and we set them up using that right hand rule to make sure that our I is around in a clockwise direction from J. And this is the usual, this is the norm, number 1. But you know, inclined plane, we get number 2, and maybe in other variations of an inclined plane we get number 3, or maybe other situations. So it depends on the context. Once we set it up though, and in this question I've got my standard I and J as horizontal vertical, you'll see that I've drawn my little dotted lines in to represent that horizontal line, and now I can determine particular angles, theta 2, I'll call this theta 1, and use those angles, or this one can be theta 3, and the overall force that's operating in that direction, which will be the length of the hypotenuse, and then I can apply those in component form, because the horizontal component here is F1 cos theta 1, and the vertical component is F1 sine theta 1, F1i and F1j. So I can build an understanding and then put them together into I and J components. And that's called resolving my forces into their components. So let's look at an example. So in this example I've got three forces, 11 newtons, 17 newtons and 21 newtons. And I want to determine the magnitude and direction of the resultant force. And they've been laid in a diagram for me already, and I've red dotted a horizontal line. So it's important to denote that in this case I am saying that I and J are my components, and they are right angled to each other, horizontal and vertical, and I'm representing these as triangular components here. So writing this in component form, my resultant force, which itself will be a vector, is equal to the I components first. So I'll start with F1. The I component's a horizontal component, and this is my adjacent side, so cos of 30 is equal to adjacent over hypotenuse, which is F1 or 11, and so I get 11 cos 30. F2 is completely horizontal, so plus F2, which is 17, and then plus, but in this case I actually subtract. I'll have to be careful here because F3 is in the backwards direction here, so that is 21 cos of 40, and that's my I component. And then I add to that my J component. My J component is F1, which is 11, sine 30, minus, because it's going down, so in that negative J direction there, F3, which is 21 sine 40. That's my J component. I evaluate this now, and my evaluation comes up with, and I'll be nice with my rounding, 10.439346 newtons in the I direction, plus, but it actually turns out to be negative, 7.9985398 ... newtons in the J direction. And now I'm going to write those down as approximately 10.44 I minus 8J. and that's a nice rounded value. But it's always important to give an understanding and impression that you've got the right answer as well. So that's example 1, and that's our first method for resolving forces given to us and using force diagrams. The second method, which I like less, but you might like more, and this works reasonably well with 2 forces, but it really starts to break down with 3 or 4 or more forces. So it's using the head to toe vectors. So if you're told that we've got force 1 and force 2, you can do force 1 first and then follow that on by force 2. So you get this 2 directions, and then the green will be your resultant force. And then, of course, we've got non-right angle trig in play here. But there's a bit of a mucking around in my opinion. So let's do an example. 2 forces act such that one is on an angle of 40 degrees above the horizontal with a magnitude of 10 newtons. So let's draw that one. Remember, the first force doesn't really matter where you draw it. But I'm going to do it here, and I'm going to say this is 40 degrees. It's got nothing to compare itself to, and I'm not giving that indication. But the second force is on an angle of 20 degrees below the horizontal with a magnitude of 5 newtons. So it's important to recognize here that this could be the second force. It's not that big. So it's got a magnitude of 5. I'll put that on this side because it's an angle of 20 degrees below the horizontal. So my resultant force, which I'll put in green, is this one here. But I would like to note, and I'm not going to solve both of them, but this is a little bit of an ambiguous question. So I might have the first force is here. Keep in mind, if that is 40, then this is also 40. And I'll rub that out now, because the second force is 20 degrees below the diagonal, but we're not told if it goes backwards or not. So it could be there. And that could be our resultant force. So we've got to be careful. We don't actually know which one it is. But I'm going to use this one over here. Now I need to just fill in some more information. So the further information I've got is that's 20. Then this is, my diagram's going to be ruined in a second, that's 70. And if this is 40, then that's 50. And so consequently I've got a 120 degree angle with 10 newtons and 5 newtons. And so to find my magnitude, which I'll call m, I get m squared is equal to 10 squared plus 5 squared minus 2 times 10 times 5 times cos of 120. And would you believe it, cos of 120 is just negative a half, so happy days there. I end up with m squared is 175, and m is equal to the square root of 175, which is 5 root 7. And I could probably just about leave it there, but I can also say that's approximately equal to 13.23 newtons if needed. It also asks for the angle. So based on this second assumption, I can see probably that angle theta there is about 20 degrees based on my scale of the 10 and 5, and I think they're about right, but don't jump to too many conclusions just yet. But I do know 5, and if I can find this angle, then I can find theta. I also now know m and this angle, so I'm going to use the sine rule. So I want to find sine of 40 minus theta. If this is theta, the thing I'm trying to find, then this is 40 minus theta here. And that's over 5 is equal to sine of 120 over m. So I do a bit of rearranging and I get sine of 40 minus theta is equal to sine inverse of 5 times sine 120 over 5 root 7 from earlier, and that's nice, the 5 and 5 cancel out. But I do get, so that shouldn't even say sine, should it? Because I've got the sine inverse over there. I get 40 minus theta is equal to sine inverse of that. And of course, that means that 40 minus theta is equal to 19.106 ... degrees, and theta is equal to approximately 21.89 degrees above the horizontal. So it asked me for determine the magnitude and the direction of the resultant force, and it's got a magnitude of 13.23 newtons in a direction of 21.89 degrees above the horizontal. Unless, of course, it's this interpretation, which would be slightly different, and I expect that to be my resultant force. Sorry, not that won't be it. My resultant force here will be a bit bigger than 40, but this will be a bit smaller, I expect. So there we have it. That's resolving forces using force diagrams, 2 different methods, the first part of our review of forces. All the best.